Cool. So first of all, thank you, Zama, for the nice introduction, and also thank you and Ricardo for inviting me here. It's really exciting, and knowing I'm the first one, I kind of feel like the burden of making these a long, let's say, success. I hope I will not disappoint the audience with this talk about neural databases, which is a kind of new research direction that is, as you said in the introduction, is actually trying to merge, three different research areas: databases, web IR or web search, and natural language processing. This is work that has been done while I was at Facebook AI, as you said, and it is actually a joint work with these amazing set of people that you can see here. James is a PhD student at Cambridge, and it's the intern who actually implemented all the stuff and did all the experiments. And Majid and Marzieh and Alon at I'm sure many of you know, were with me at the applied research, let's say, department of Facebook AI, and Sebastian, which is a very, very famous NLP person that, helped also in the project. This is, the results of this research has been published in two papers that you can see here. One is VLB 2021 paper, where we present the main ideas, the main results, and some challenges. And the second paper is actually to be presented at ACL, and it's mainly focused on, let's say, some refinements of the results, but also on the data set that we built. All right. Okay, so I don't think I need to introduce to any of you what a database is. It's a collection of let's say, data structured under the form of tables, connected by relations. And usually you have a language where you do, insert data into your tables and relations. And then afterwards, you can actually query this data using, typically structured query language or SQL or SQL, depending on how you like to pronounce it. And, you can retrieve data from the database. And the most important thing here is that whenever you insert data in your database, you have to consider the structure of the database itself. So whenever you insert new people, for instance, in the people database, in the people table, you need to add typically you can have like these three features, like the ID, the name, and the country. And then it's important that, you always insert data under that form. So this actually constitutes I would say, the core of a database system, which is the schema. So you have to have a schema, and the schema is very rigid, and it describes the structure of your data, and it is usually described in a formal language, and also insert and queries are done in a formal language according to the schema of the database, right? So what we actually did was the following. Can we remove the schema from a database? It looks like a very, very, let's say, I would say, a bold question to ask, right? Because, as I said, the schema is the foundation of a database, and it's a place where, you can structure your data. And we wanted to say, okay, let's remove it. And how can you do it? Well, instead of considering data as a, let's say, formal ways, a set of relations, we consider our data as a set of facts. So you can read some facts over there. So Sarah married John, John works at Shell, Sarah is a doctor, and so on and so forth. And then we have a neural query processor. So we remove the schema, let's say, jet manager, but we have a query processor that is a neural component. So we follow the trend of the last 10 years, and we kind of try to transform a query processor into a neural query processor. And then the hope is that once you start asking queries such as who is French, the neural query processor will actually exploit some kind of internal knowledge to, for instance, reply that Sarah is French because Sarah is from France. And you can actually say who lives in USA, and Marcelo, of course, lives in USA, but also Rui, because Rui lives in Palo Alto, who is likely to be in USA, unless, I mean, I'm sure there exist other Palo Altos in the world, but let's suppose it's the most likely one. And the same is who works at Shell, right? Because Louis works with John and John works at Shell. Both John and Louis are, let's say, answers to these. Of course, I have not yet introduced other kind of queries that we are actually trying to do. I don't want to like, spoil or waste the surprise, spoil the surprise. But of course, as you can imagine, we want also to do aggregation and counting, but those were not shown in the example. Okay, so first of all, let me clear the table here. We are not doing Q&A, although the system, or better, the problem looks similar. And the main difference, if you will, is that typically in Q&A, you do look for an answer that is contained in a sentence in a document. And even if it's the result of, let's say, the combination of a couple of sentences, they're usually local. Here instead, we are interested in finding answers that might be scattered all over the places. And, you might need to do kind of joint. So like multi-hop query answers, which is actually a research area in natural language processing. But it's, again, a little bit different because multi-hops here can be done across different facts that can be scattered all over the places. And actually these, let's say, being scattered all over the place is another challenge because you might have a very large fact, database of facts, and therefore these might pose like some challenges as well. All right, so as you can imagine, or maybe you've already read some of the papers we have published, we adopted, I would say, de facto standard solution, which is that of using a transformer. The most typical, the most famous incarnation of transformers for NLP is BERT, which is basically a context-aware word embedding, or let's say very large language models. They have received a huge amount of attention. Sorry for the pun, but they are basically ubiquitous. And in the last months, they've actually started to be used also in computer vision with vision transformers and subsequent, let's say, improvements to the model. Again, I will not go into the details, but the main idea of this kind of language models is that you basically enter a sentence or a sequence of tokens, and the model computes the importance of each token with respect to the others. And this importance, which is captured by the concept of attention in neural network, constitutes the representation of those words. Now, these very large language models are trained, and here I'm actually listing some of the ways large language models are trained on, in a self-supervised fashion, are trained in several different ways, right? So, for instance, the first work that was that of BERT it was called masked language model because they tried to kind of, let's say, guess, which were the words masked in the original sentence, or they wanted to guess which was the next sentence. And here I'm listing some of the possible solutions. So here we took advantage of this kind of technology. And in particular, we took advantage of a technology that has been published and let's say used by Google. It's called the text-to-text transfer transformer, or T5 for friends, which extends the concept of self-supervision to actually multitasking, where multitasking is done both on the self-supervision, let's say, part, where you basically train on different self-supervised tasks, but also on, let's say, supervised tasks. Here, I list some of them. Translation is one, natural language inference is another one, and you name it. I mean, there are several tasks. And what's the idea? Why we want to do that? Well, because the hope, and we see that actually, experiments confirm these hypotheses, is that once you train this large language model with a lot of data, they actually memorize some of the relations, they memorize some of the knowledge extracted from the data on which they were trained, that can be used in downstream tasks, for instance, the neural database. And in particular, this T5 model is actually training on these very, very challenging tasks of inference or translation. And that we will see for neural databases are very important. So having given this introduction, let me show you what is the task we are proposing with the neural database. So the task is the following. Given a query and a small number of facts from the database, can neural database, or T5 in this case, accurately answer queries that are posed in natural language? So here, the input that we want to use is a query and a set of facts. So you can think of, let's say, the task as given a query and a set of facts, can I translate this sequence of tokens into the answer to the query? So this is the task. And in fact, we were challenged also with the task of building a data set on which to train and test these kind of ideas. And so part of this research was also spent in building the data set. And I would say the bulk of the ACL papers is on how we are building the data set. And we are going to show some of the details in the next slides. So here, just to visually describe what a query is in this case, right? Consider this example. You have, in this case, 8 out of 500 facts shown, and you can read them. And then with these facts, you want to be able to answer queries such as list everyone born before 1980. And this is what is usually called a set query, which means you want to retrieve a set of results. This is the typical select, star from. Or whose spouse is a doctor? This is a join, right? Because you want to retrieve, let's say, people, and then you want to follow the relation, being a spouse of, and then another relation being a doctor. And this is a typical join query in traditional databases. But as you can see here, we just want to answer this query using a natural language question. Who is the oldest person? This is, as you can imagine, a very challenging task for a neural database, because now you have to understand that you want to find the argmax of a function, and the function is age of. So, or the argmax of a relation in this case, and the relation is age of, or born in. So you still have, some kind of mathematics to do here. And of course, you might also end up with null null result sets, like who's Sherry's mother, you don't know from the facts. Mind the fact that you always want to retrieve your answer from the facts. And of course, I mean, one possible extension would be to retrieve answers from the implicit knowledge base that is stored in the large language model. But in these works, we didn't take care of that. So as I said, we needed to generate a data set. We actually are releasing this data set along with the ACL paper. The data set is called Wiki NLDB, and it's built automatically from another actually Google technique, which is Kelm. So Kelm is a set of facts, let's say natural language facts, and let's say we use those facts to actually build triples, and in order to make sure because using triples we can actually compute the correct answer to the queries. Now, again, the goal is to build samples in the form that are shown in this paper. Sorry, this slide. So D, Q, and A, D is a set of facts or the database, Q is a query, and A is the correct answer. So given facts in D and the query in Q, we want to build or to generate the correct answer. As I said, we wanted to use Wikidata, but instead of starting from Wikidata, we actually started from Kelm. Kelm is a basically list, is a huge list of let's say sentences that have been generated automatically from Wikidata, and we actually do the inverse mapping from the target sentence to the input triples, because then we can actually compute the correct answer. So remember that the only reason why we want to go from target sentence to input triples is because we want to first, build a set of facts from the input triples, of course, but also because we want to be able to generate or to compute the correct answer. And here you can see some of let's say the input triples that were generated from the target sentence. All right, and the paper where Kelm is actually shown and described is that one that you see in this slide. And Kelm, there was a very nice blog post like a week or two ago on Kelm. All right, so we saw how to generate, the facts. How do we generate queries? Well, again, we started from some templates. So in this case, we are really biasing. Well, we are somewhat biasing our queries towards 7 large categories. But we wanted, so queries can be, let's say, as easy as when X was born. So when Ricardo Baeza Yates was born, or where does Usama work? So these kind of queries, which are implicitly describing triples such as X born in Y or X employed by Y. But as you can imagine, we wanted to generate also join queries, and we did that by chaining triples. So if we have Y located in Z and X employed by Y, we generate the query, does X work at a company based in Z, right? So this is the main idea. And of course, you can generate things such as, is the child younger than Y? So all that kind of complicated combinations of things. And those are, once you define these templates, you can automatically generate those queries. So here are some example queries. So in this case, we wanted to generate a set query. And a possible query is who studied at University of Minnesota. And here are the supporting facts. So we know what are the facts that will help answer the query. And the answer is listed in the last row of this example. And mind the fact that these supporting facts are the facts supporting the answer. But these are not necessarily the only input to NeuralDB. I want to stress these. These are the supporting facts, and it's an important concept. This is the concept of facts that should be used to actually reply to the query, to the question. You might have, as I was saying, more interesting cases such as count queries. So how many people work for Yale Law School? And these are the two supporting facts. And given the number of supporting facts, the answer is 2. And you can actually answer min max. So what is the largest yearly attendance? And you have like 25 facts that are relevant, pertinent to this query. And the answer is the one that it's listed there, because the database is able to take the max out of there. And then Boolean queries, is North Carolina State University the employer of Westmore? There is a supporting fact, and the answer is true. And then you have join, as I was saying, this already sort of understood example, who plays for a team in League One. And then you can see this fact that is actually mentioning that Thomas Alofs played in RC Strasbourg Alsace, that is a football club in League One. And so these two things combined are defining the answer, which is Thomas Alofs. Now, as I said, there is automatic generation of these facts and query, facts plus query samples. And as you can imagine, as I said, we want to input these these to a transformer. And as you know, transformers only accepts a fixed length sequence of tokens. And so we generated variable lengths. So DB sizes is the number of facts or supporting, of facts that are generated, and from which we retrieve first support sets and then the answer. And as you can see, here is the distribution of, let's say, queries with given a certain number of support sets. And of course, you cannot have support sets set larger than 25, because in this case, the DB size is 25. And on the right-hand side, you can see the query types. So bool, set, count, min, and max. And for each query type, the percentage or the fraction of queries for which you require a join or for which you don't. And so we generated different sizes, 100. I'm just going through these, 250, 1,000, and 2,500. And our experiments are testing, testing the effectiveness of NeuralDB, varying also the DB size, because as I said, it's a very important factor in the performance of the NeuralDB. All right, so this is the data set, right? So we have seen what's our task, and we have seen how to build a large scale and, let's say, I would say wide, with respect to the number of topics, data set, right? But now, how do you actually want to answer those queries, right? So here's the first attempt that we tried. Of course, it's a baseline, and we wanted to understand, how this solution, which is a sort of, off-the-shelf solution, out-of-the-box solution, which is basically just using T5 transformers as the neural query processor. So here the task was simple. We fine-tuned a T5 model, right? On the task, on the samples that we generated in Wiki and NLDB, right? So now you input the facts, you You input the query and you hope that you will get the best result. Now, as you can imagine, these kind of transformers should also be able to answer queries such as how many people lives in USA. And maybe this is not the best, but you know, I don't want to spoil the results. So here's the first attempt at measuring the accuracy of our system. So first of all, accuracy in our system is simply the number of times we can exactly answer a query. So for instance, if you ask for number of people living in US and the answer is 10, but your NLDB, NDB answer 9, the answer is not correct. Now, again, in many settings, the answer is not correct, of course, but in other settings, you might not be interested in being super accurate, but you want to trade some accuracy off for the flexibility that NeuralDB is offering. And these examples here are actually also showing what happens if, so let's forget for a second about perfect IR and WholeDB fusion, the last two columns. Let's focus on perfect IR and WholeDB. So WholeDB consists in feeding to the T5 transformer all of the fact base. And in this case, we can only try our solution with 25 facts because larger fact bases do not fit in traditional transformers. And as you can see, if we feed the whole database, the accuracy in the case of, let's say, all right, so let's focus on the right-hand side plot for a second. Here is, we are showing the EM accuracy for different types of queries. As you can see, in the case of Boolean queries, so true and false, the accuracy is 1. So we can always retrieve or generate the correct answer. And perfect IR is actually a strategy that consists in a sort of oracle strategies. That is, we know which facts are necessary to answer the query. So we only feed to the transformer those facts. Whereas WholeDB is the opposite. We feed to the T5 all of the facts. So as you can see, the lowest performing type of queries are, let's say, min max. But even in those cases, with perfect IR, we score almost 0.9, which is extremely high if you think about it. So without requiring any DBMS or anything, we just require transformers. You can answer 90% of the times correctly. We actually did a manual check, and the incorrect answers were very close, usually +1 or -1 with respect to the correct answer. Same for count. We are doing a little bit better than min-max, and same for set. And in all the cases, it's clear that a good retrieval strategy, a good information retrieval strategy will help in answering the queries. The left-hand side, let's say it's divided by the size of the support set. And as expected, the larger the support set size, the lower the accuracy. This is kind of expected because, the transformer has to do multiple, let's say, interleaved, let's say, reasoning. And this actually also confirms the difference with the Q&A task that I was highlighting at the beginning. Now, again, we also tried different strategies. Different from T5. We tried long former, to reduce the computational requirements. The long former is more efficient and can also take care of longer range relationships between sentences. But as you can see, it's not as performant as T5 in all the cases. And it's let's say the main result here is that you basically need a good IR strategy to retrieve the best possible set of answers. All right, so we have seen a baseline, and there are several issues with this baseline, but the two outstanding ones are, first, that transformers cannot deal with large fact bases. In our experiment, in the baseline experiment, we only use 25. And second, they are not good at doing aggregations, essentially. So let's see what we did in order to correct that. So we have several challenges. So scale, as I was saying, large scale fact base are not, is a challenge for neural database. Multiple answer spans. So neural database might need to generate thousands or hundreds of thousands facts and aggregate over them, and locality is not there, and multi-hop and conditioned retrieval might be used. So in order to answer a query, you might need to retrieve facts on the basis of already retrieved facts. So, to actually answer these challenges, we kind of designed these, and this is like the real NeuralDB architecture that is trying to, let's say, divide the query processing phase into three main sub-phases. The first one is the support set generator, and this is the IR component. It could be TF-IDF, it could be dense retrieval, but it's essentially an IR component. Once you have generated your support set, you are using Neural SPJ. SPJ stands for select, project, and join. So this Neural SPJ is the neural, equivalent to the database component, So this is the neural equivalent to the query processor in databases. And then you have, it is using NLP techniques in order to generate, to do the select, project, and join. So, and then this is a traditional database component, which is computing the aggregation. So average, sum, mean, max, those are typical aggregation mechanisms. This is not, not neural, I would say. And so now you're able to basically feed this system with the facts and the query, and the facts only go through the support set generator, whereas the query is inputted to all of the three phases. So the query is used in the support set generator to, retrieve the supporting facts. The query is used in the Neural SPJ to understand, first, which kind of query, set, argmax, argmean, whatever. And second, to actually output the data that can be then used in the aggregation phase. And the aggregation phase, again, is using the query to know which kind of aggregation you need to do. To actually deal with the issue of scalability, we are replicating the Neural SPJ component. What does it mean? It means that the support set generator actually generates different support subsets, one for each possible answer. So in this query, for instance, how many people's spouses are doctor, right? You see that Sarah married John and John works at Shell. So here we have a spouse relationship, and the second one is as well a spouse relationship. And then the Neural SPJ is trying to understand if, let's say one person works as a doctor, like one person's spouse works as a doctor, right? So in the first case, the Neural SPJ returns null because none of them is a doctor. And the second one actually returns John because John is married to a doctor. And so the aggregation simply counts the number of not null entries in these let's say, query-based derivation of the support sets. Now, without going into details, also the support set generator, as I said, I already hinted at it, is not a simple retrieval thing, but it's more like I would say it reminds of query refinement of Rocchio, Rocchio algorithms to do query expansion. That is, you retrieve a first set of facts, and you try to understand. This is the SSG classifier. You try to understand if the set of facts is relevant for your query. If not, you go ahead and retrieve again, more facts, and you repeat these until your classifier says stop. I mean, this is enough. And then you split these selected facts and you send them to the Neural SPJ. The Neural SPJ is, this is really like a simple, transformer, simple transformer component trained on the task trained on different tasks that depend on the query type. So for Boolean answers, you seek to generate binary values. For count set queries, you want to generate all the entities. And for argmin and argmax operators, you want to generate key value pairs, because, for instance, if you want to say which place has the highest yearly number of visitors, you want to compute key value pairs under the form place number of visitors, so that you do the max on the value side and you retrieve the key side of this pair. And so these are like examples of Neural SPJ outputs. So for a query, does Nicholas' spouse live in Washington, DC? The output is Nicholas lives in Washington, DC with Cheryl. Cheryl is a Nicholas spouse. This is the retrieval phase, and the answer is true. So this is the output of the SPJ. Who's the oldest person in the database? Tuvo was born in 1912. So for that fact, for that supporting fact, you retrieve the key value pair Tuvo 1912. And for the query, does Nicholas' spouse live in Washington, DC? You have that Tuvo was born in 1912. So this is not relevant for the query. So the answer is no. So how these perform actually when compared to the other component. So you remember I showed you some results, and these are actually like numbers associated with those results. So if you use TF-IDF to retrieve facts, the first thing that should be highlighted is that for min-max queries, TF-IDF plus T5 has an accuracy of 0. And dense retrieval, DPR, plus T5. So dense retrieval is basically embedding query and documents and retrieving based on the dot products between these queries and documents. And even in this case, the accuracy for min-max is very low. But for NeuralDB, when you split the phases into the 3 phases that I just showed, this actually goes to 100%. And also the count queries, although we are not doing 100% exact match accuracy, we are almost, in many cases, more than doubling the performance of both TF-IDF and DPR. And the trend is kind of confirmed. Atomic results are easier. So if you have let's say doing retrieval plus T5 is already enough. And also in the case of joins, the increase in terms of accuracy is not as large as the other cases. But still, it is substantial. And 2 things here. First, let's say neural database, of course, it doesn't generate always the correct answer, but it's getting very, very close, except count and joins, which still requires some research. So, 2 good news. One is that, yes, neural databases maybe have a future. Second, also research on neural database has a future, because there are some gaps that need to be closed. And also another thing is that one question that you might have is the following. All right, so SPJ performs very well in the case of results that are correctly retrieved. But how does it work, or does performance degrade in the case of non-perfect retrieval? Well, remember that we train end-to-end the architecture. So we train the SPJ to be robust to this kind of errors. And so when you don't have perfect IR, so perfect retrieval in the first phase, you still get very good results. Basically, let's say the same results as perfect IR. Numbers here are different, if you're wondering, because here are results on around 25 facts. The others were on larger databases. This is a breakdown on, let's say, on different kind of queries. And also, let's say, we also tried a different kind of match strategy, but results were not that different. So basically, soft match means, we look at the answer and we try to see if they are close or not. So in some cases, results are better, in particular in terms of precision, but in the case of join, the precision in the case of join, but in general, they are not that different. And here are the results according to different database sizes. As expected, the larger the database, the more challenging the task becomes. So this actually shows that there is still some research to be done in the retrieval phase as well, because when the size of the database, of the fact base increases, it's important to have a good retrieval strategy. So the precision really matters. Again, you can read the results, but it's kind of impressive, at least to us, that the exact match accuracy is steadily above 0.8 in the case of small to mid-sized databases. And of course, it degrades with the size of the database, as I said. But again, when the number of supporting facts is small, say in the order of 5 or less, the accuracy is still pretty high in this case. All right, so I think I had 45 minutes, and I guess I'm on at time. And here are some conclusions and future work that are interesting. So first of all, we described this architecture of neural database, and in particular, we are the first to propose this task of trying to solve database queries without a schema, without an underlying schema. So as you can imagine, there is still a huge amount of work to be done. And there is, in particular, a lot of exciting work to be done in order to close the gap with neural databases. Of course, although this is not was not our primary focus, that is being as close as possible, being exactly like like traditional databases, we want to be as close as possible. There are issues here. Let me tell you right away. First of all, and I'm not just saying that because, Ricardo is listening, but there are biases in our language models, because we know that there are biases in our language models. And these might impact the results. In particular, we don't want our database to automatically infer that, I don't know, a female is a nurse, whereas a male is a doctor, and things like that. So this is something we still need to address. And there is another exciting, in my opinion, open problem here, which is how to deal with updates. So I didn't mention these, but of course, a fact base being a dynamic fact base, because now you can retrieve facts, it can grow over time, right? So you can add things that might be controversial or things that are not non-controversial. For instance, if you first had a fact that was Mariah is unemployed, and then you have a fact that is an additional fact, Mariah works for Apple, Mariah is not unemployed anymore. So Mariah now works at Apple. But instead, if you have a fact like Casper likes tea, and then you subsequently add a fact like Casper likes coffee, these two things are not in contradiction one each other. So if you want to know which kind of beverages Casper likes, he likes both tea and coffee. And that's it from me. And I'm really looking forward to your questions. Let me stop sharing. And
thank you, Fabrizio. A really interesting talk. And I like both challenges, like get rid of the schema. So I already have some questions, and I will start with the most frequent question because I think two people are asking the same. So both Antonio and John, they are saying, do you retrieve correct answers which are in the generated facts and not in the supporting facts, on the original facts? And the answer is yes, this is not exactly like a database because you are answering more things than a database.
No. Okay, so I think I mentioned this at some point. In this particular, let's say, version of Neural Database, we are only retrieving facts and answering queries on the basis of the retrieved facts. The role that the knowledge base is playing is in implicitly modeling relations. So the knowledge, like T5, for instance, is, it contains some knowledge about the relationships, contained in the training data. We are exploiting those relationships, but not, let's say, the knowledge from, but of course, you can actually cheat, as somebody was mentioning, and you could actually answer more queries than those contained in the database.
So that will be more like a deductive database.
Exactly.
No, that's very interesting. So
yes.
Maybe you can answer things that are not answered by a relational database, and also you can miss things that the neural database will not find.
So, if I can add something, because I also forgot to mention this at the end, but another interesting direction is that in traditional database, you have data, of course, but here, thanks to the fact that transformers are pervasive in both NLP and computer vision and sound and whatever, you could actually now mix things like multimodalities, like multiple modalities. You can answer queries about pictures, joining the facts contained in pictures with facts in neural language. And this is like unlocking a totally new potential for database. This cannot be supported by traditional database.
Well, there was an early question in the chat that I think you already answered, but just to make sure. So like Jen G asked if in the sample queries slide, how did you get those facts? I think those come from the wiki NLDB database, and do you know how they generated those facts, or are users?
No, okay. So the facts are contained in the wiki NLDB database, but they have been generated by Kelm, let's say, sentences. So Kelm is a Google product, and it contains lists of sentences that are the result of reasoning over Wikidata triples. So we do a sort of reverse engineering from those things, because we want to make sure we are getting like the exact answer to queries, and so we are exploiting.
So that's the way that you know the answer. You know the correct answer.
Exactly.
Great. Yes. Also, Antonio asked an early question. Was a typical DB is used to retrieve data, which is supposed to be static. Do you also aim to retrieve generated data, or let's say maybe even streaming data?
Yes, why not? I mean, again, Now I don't, okay, I don't not work at Facebook anymore, so I don't know, I mean, how this project evolved internally. I can only tell you, let's say, how, let's say, it was in, okay, so the main ideator, as you can imagine, of this was Alon, that comes from the database community. And, you know, he was the one, let's say, proposing this thing. And the idea was to go beyond databases. So the first step was to remove the schema. And this was already, as I said, a bold, let's say, challenge. But then you actually, once you have succeeded in that, you can add things that other database cannot do. For instance, answer queries on generated things. So, but this comes with additional challenges because you don't want hallucinated things to be false or wrong or biased.
Yeah. So John also was asking if you get the supporting facts as part of the result of the query, and I guess the answer is yes.
Yes.
Yes, of course.
So wait, the supporting facts. So there are two supporting facts: the one in the ground truth and the one we generate. Yes, of course we also get the ones that we generate.
Yeah. So just to go back to the first question, basically you remove from the answer all the facts that are not in the original facts.
We do not remove. It's an IR thing. So we are not generating things that are not in the fact base.
Okay, so you have like that check. So John has another question. Basically, any information on the running time of queries. So this is faster or slower than a traditional database, and also the power requirements. So you can use the same computer as a relational database, or do you need a powerful, let's say, cluster with GPUs?
So okay, let me answer both questions. So first, let me start from the end. So the last one. So you can use distilled models, and then you can use CPUs. Of course, you lose a little bit of quality at the moment, but you can run these queries on, you can answer these queries on traditional hardware, not necessarily GPUs. And second, let's say the first question, what's the power requirement? Well, consider that we only do fine tuning, and we are not actually, you require GPUs, of course, but it's not like, I mean, the training doesn't run for weeks. It runs for hours. And then at runtime, it's kind of quick. I mean, it's in the order of seconds, of course. It's still not as quick as a database. But as I said, I mean, this unlocks additional potential. So at the moment, we are more interested in, let's say, showing that we can get rid of schema. We kind of did. And now, you know, like there are several directions, and one of them is, of course, efficiency, which is close to my heart as well, as you know.
I think we have also a question from Martin. So what about NoSQL databases? I mean, with a flexible schema.
Okay. All right. So true, they are flexible in the sense that in the payload, you can add JSON, data, and you can basically, still kind of represent things that you didn't have in the original data. True, but at the insert time and also query time, you need to know the schema, right? So you cannot answer queries that are not supported by the schema. In this kind of database, instead, you can. Well, we hope you will be able to do the same, but I mean, again, 80% of the time you can, the times you can at the moment.
So great. I think we cover all the questions, and we are perfect on time. So it's just 1 hour. So thank you again, Fabrizio, for a very interesting talk. I think this is like a complete different view of the problem, and it's always good to do that. Maybe we have a last question. Oh no. So okay, sorry. We have the last one. So Giuseppe, a very nice talk. What about comparison integration triple stores, RDF, proposed by the semantic web community? So we have all possible database views here in the talk.
No, we didn't think about that. But if Giuseppe is the same Giuseppe in the list of participants, I think we can work on it. We are on the same, yes, on the same department. No, it's actually a very interesting direction. It's actually a very interesting direction, and there is a sort of novel branch in artificial intelligence, which is represented by neural symbolic AI, and I guess that adding symbolic methods to neural database is key to actually achieve, let's say, I would say almost parity with traditional database without, again, requiring the schema there. But it's a great question, actually. Yeah, thanks, Giuseppe. Sorry. Yeah.
So you have future work for all the other type of databases. Thank you again, Fabrizio, and a very nice talk. And
thank you.
I hope to see you soon in person.
Yes, I hope so.
So thank you for all the participants coming. And remember, every month we have 2 talks, one highlighting research from great people like Fabrizio, and also highlighting research from people in Northeastern University. Bye-bye.
Thank you.